So, good evening, everyone. Welcome to the summary session related to structure analysis course. So, this session is an additional session related to what you have covered in all the current, or you can say previous feeds related to the structure analysis course. This session will give you an overview of all the numerical problems that you have solved related to the structure analysis. In this, we will start from the week 1 till week 12, that topics you have covered in the whole problem solving session that we have covered in every Saturday regarding the structure analysis course. So let me share my screen first, then we will discuss each and every question, and that will revise your concepts related to this course. I hope the screen will be visible to everyone. So let's start the session. So I welcome you all in this summary session. So introducing myself, my name is Pranam Mahajan. I am a PMRF scholar in Department of Civil Engineering from IIT Madras. So NPTEL has given us this opportunity to help you in solving the problems related to the topics that you have covered in all the weeks that this course is going on. But now, as we have reached to the end of this course, so a special session was conducted in which a summary of all the weeks, or you can say all the topics that you have covered in the last 12 weeks, we will discuss upon that. So let's start this session. So again, I am giving you an overview regarding what you have covered in last 12 weeks, as I used to give in every week when the class used to start. So starting about this course, I generally used to bifurcate this course into two parts. One is the analysis of determinate structures, and another is analysis of indeterminate structures. So analysis of determinate structures depends upon the number of available equations to you, depend minus the number of unknown reactions, or you can say number of unknown reactions minus the number of available equations. If the number of available equations are equal to the number of reaction unknowns to you in this case, so in this case, then you will get the degree of static indeterminacy to be equal to 0. Then only you can tell that the structure is statically determinate. Else, if any other degree will come into picture, you will tell the structure is statically indeterminate. So for this, we have as a fundamental structures, three fundamentals we have. One is truss, second is beam, third is frames. So the general difference we used to observe in a beam and a truss is that a truss don't have any bending moment in the member, whereas beam can have shear force as well as bending moment along the length of the member. Now, if you talk about the difference in beam and frame, so mechanically there is no difference, but physically, if you want to see, we can say that frame for the current situation, we are looking, that frame is a two-dimensional element, whereas beam is a one-dimensional element. Now, talking about the analysis, we have different methods to analyze either frame, either truss, either beam. So we started with analysis of truss by two methods. One is method of joints, another is method of section. Whereas if you want to determine the deflection in the truss, you utilize the principle of virtual load, and using that we have derived one equation. From this, if your delta at any point you have to require, what you will do, you will take summation of n, capital N, small n, multiply by the length of the member divided by the axial rigidity, that is AAE. Further, for deflection of beams and frames, we have different method for the analysis. One is moment area method, conjugate beam method, direct integration method, maculae method, and principle of virtual load. So it's not like that you have to specify only one method. So, but depending upon the type or the complexity of the problem, you can use any one of the method that is easier for you to analyze the structure. After that, we move to influence line diagram. So in what cases influence line diagram is used? When you have moving loads that is traversing over a structure, or you can say moving from one place to another. Under such situation, under where you are experiencing maximum bending moment, maximum shear force, or reaction at different supports. So under that situation, you apply influence line diagram, wherein we use a principle called as Mueller-Bridge law principle, and using that we use to analyze the structure based upon the moving load. After that, we have moved to the degree analysis of indeterminate structures. So, what are indeterminate structures? Those have degree of static indeterminacy greater than zero. It could be one, two, and many more. So, in that situation, we use analysis of indeterminate structure. So, for that also, we have different methods available. For truss, we use method of consistent deformation, which is also based upon, you can say, principle of virtual work. After that, we have seen for beams and frames, you have slope deflection method, you have uh, moment distribution method, you have you have method of consistent deformation. So these are the methods that are available for the analysis of beams and frames. And finally, we have introduced to you about the stiffness matrix, as well as the the, you can say, displacement stiffness matrix and flexibility matrix, wherein stiffness matrix is based upon the displacement method principle, whereas the flexibility method is based upon the force method principle. So let's start few problems. So we will look about each and every problem that we have covered in all the 12 weeks. This will refresh your all the concept and will help you in, you can say, you have NPTEL exam. Those who are not given, for them it is a refreshing kind of a session. But for those who are giving the NPTEL exam, they can use them as a part of revision for the exam that to be held in the coming days. So in the first week, we started with fundamentals from the strength of materials. We started with static equilibrium, wherein we have seen how to calculate bending moment and shear force diagram for different structures. Okay, so let's see one problem. So in the first problem, we have seen, or you can say, in the first problem of this session, in this you are given a structure which is having an overhand section. In the overhand section, it is applied an anti-clockwise moment of 5 kilonewton meter, and in the rest of the portion where you have simply supported load, in that you are having a uniformly distributed load over the length of 5 meter. So what is asked to you? So in the question, it is asked to you to calculate maximum positive and the negative bending moments. So for the bending moments, first is the basic concept is you need to require to calculate what are the reactions, what are the unknowns in that this system. So unknowns, or you can say constraint that are provided by the supports, that we are needed to calculate first. So first step is to calculate the reactions or the moments that are coming due to the presence of the supports. So for this, what we will do, we will apply the static equilibrium equations. So we have three equilibrium equations: summation of vertical forces, and summation of horizontal forces, and summation of moment about any point to be equal to zero. So when we apply summation of vertical forces to be equal to zero, we got the sum of reactions, that is RB plus RC, to be equal to 50 kilonewton. Now both are unknowns. We require one more equation that will give us uh, one more equation to solve these two unknowns. So we applied summation of moment about any point to be equal to zero, in which we have taken all the clockwise moments to be positive and all the anti-clockwise moment to be negative. And when we did and simplified everything, we got the reaction RB to be equal to 26 kilonewton. Now, after calculating reaction B, when we substitute back in the equation number 1, wherein you have summation of reaction to be equal to 50, then we got the reaction RC to be equal to 27 kilonewton. Now, the question is asking you to calculate the maximum bend holding and the maximum sliding moment. So what you will do in this case, you will define the moment equation about any section. So let's say we have taken H section, which is in between the UDL that you have applied over the section, and we are determining this from the left of the section. So if you apply this concept, you have the moment due to, I think we have applied from the right of the section. So in this case, if you apply from the right of the section, you have 24h coming out from the reaction of RC, minus 10h into h by 2 is coming out from the UDL that is applied over the system. Now this is the equation of the moment at any particular point in the section. Now, to determine the maximum and minimum value, what we used to do, we used to differentiate the equation and get to know the points at which the equation will come out to be maximum and minimum. So we have done that, and from this we got the value of x to be equal to 2.4 meter. Now another step we can do is to further do the differentiation, and then if it is coming out to be, and if the double differentiation is coming out to be greater than 0, then we tell that equation is minima, or when the double differentiation is coming out less than 0, we tell the equation to be a maximum point. But in this case we have 1 point. Now we are expecting to calculate what is the value at that particular point. So substituting this 2.4 in the equation of mx, we got the value of moment to be equal to 28.8 kilonewton meter. Okay. Now we again draw the bending moment diagram. So as we already know, the bending moment diagram for this UDL is a parabolic surface, or you can say 2-degree surface. So in this you have seen that at x is equal to 2.4, at near about the middle of the 2.5, you are getting the bending moment value to be equal to 28.8. That's why you have made the parabolic section. And in the AB section, it is coming out to be anti-clockwise moment concentrated at A. So that will give you a constant line till A for the AB section, and that's why the the slope of that line is constant. And when you join all of them, you will get to know the bending moment profile of the whole section. So from this you can conclude that maximum Hodgin moment is coming out as minus 5 kilonewton meter, and maximum sliding moment is coming out as positive, equal to 28.8 kilonewton meter. Fine. So this is the overview of the what we have covered for the bending moment in shear force diagram. Now let's move to the analysis of trusses when it is statically determinate. Okay. In this, one more concept is there for trusses. So when you have the stability of the truss to be, or you can say degree of static indeterminacy to be equal to 0. So how you determine the degree of static indeterminacy in case of truss? You have one equation that is uh, sum of members, that is m plus r minus 2j. Okay, where m is the number of members, r is the number of reaction, and 2j is the j, in which j is the number of joints. So for the stability of truss, if that ds will come out to be equal to 0, we tell the structure to be just stable. When this ds is coming out to be greater than 0, it is stable, and when it is less than 0, it is unstable. But this criteria will give you one value, but you can't directly use this value as a concept. You have to see yourself also. Then when you remove, or when you place the load in that particular situation, will the truss be stable or not? That will also define, because sometimes mathematical equation will give you the value that will be stable, but in actual it should not be stable. Okay. So let's see one of the problem. So in this problem, you are giving a truss and you are solving it by using method of joints. Okay. So in this, it is told to you to calculate the force in the member AF and DE. Okay, so what you will do? First step, calculate unknowns. So unknowns are your reactions. You already have seen that this is a simply supported truss. In simply supported truss, your degree of static indeterminacy is equal to 0. After that, you will apply the equilibrium equations, and then we got the value of horizontal reaction at A equal to 30 kilonewton. And similarly, if you use vertical summation of vertical reaction as well as moment about a point, we got the reaction value as at C to be equal to 24.9 and the reaction value at A equal to minus 0.49, or you can say minus 0.5. Now after determining all the reactions, we will move from point A, or you can say from each joint till the point we have determined all the forces in the member. So starting from the joint A, if we draw the free body diagram of the joint A, and after that we apply the equilibrium equation. So in equilibrium equation at joint A, we are using summation of vertical forces to be equal to 0. When summation of vertical forces to be equal to 0, if we have applied, we got to know one value, that is the value in the force member AF, that is coming out to be equal to 0.585658 kilonewton. After that, when we applied summation of horizontal forces to be equal to 0, then we got the value of other member, that is AB, equal to 29.7171 kilonewton. Okay. After that, we move to another joint, that is your joint F, in which again, if you apply summation of vertical and horizontal forces to be equal to 0, same we got to know the value of unknown members, that is equal to, for FB member it is coming out to be minus 0.5858, where minus is coming indicating you that the member force is compressive, because in this free body diagram we have assumed that the outward, or you can say positive, value of the force is considered to be tensile. Okay. After that, we have calculated another unknown at joint C, that is for FE member force, that comes out to be equal to minus 29.5 kilonewton. Then we move to joint E, and from joint E, we calculate the value of horizontal and vertical forces to be equal to 0. And from that, we got to know the value of ED and to EF to be equal to minus 29.5 kilonewton, which is a compressive force. Okay, from this we got to know all the two forces that are asked in the question. And in the similar way, if you want to calculate all the member forces, you can move to each and every joint and then calculate the member forces using equilibrium equations. Okay, so this is how we use method of joints in particular section. Now talking about, if I talk about in what situation you have to use method of joint and in what situation you have to use method of section. So method of joint is a simple task when you have to determine at each and every joint. Then it's easy to use method of joints, because in that one simple methodology you have to use that. Take any joint, use equilibrium equation, dot get to know the unknown two forces, and then in the similar way proceed till whole truss is determined. But in what situations we use method of sections? So when your truss is very complex and we need to know only the force at the middle of the member, or at very far end, at a very far place from the end of the member, in that case you don't need to use the method of joints, wherein you will calculate all the forces and till the point you reach the place where the member force you have to calculate. Under such situation where structures is very complex and you need only one member force to calculate the value, in that you will cut the member, you will see at what point almost all the value of moments are coming out to be equal to 0 and one unknown will be remaining, and from using that you will calculate the value of unknown of one force, and then the nearby elements force you can calculate using method of joint. Under such situations only we use method of section. Now talking about how you will analyze the truss when you have to determine the vertical and the horizontal deflection in the trusses. So we have method of virtual word. So in this method of virtual word, you have some steps that you are required to follow. Actually, these steps are defined based upon the principle of virtual word. So what you need to do, first determine all the external forces in the member, that is the number of reactions that is there in the structure. Now, what you need to do, you need to remove all the external forces and apply a unit load where deflection is required to calculate. So in the first step, what you will do, you will remove or you will determine all the forces in the member like you did in the previous question. You can use any method, either method of joint or method of section, and then you can use any method to determine the external forces. Okay. After that, under at what point, suppose at point E, let's say I am assuming to determine the vertical or the horizontal direction. So if I am expecting to calculate vertical deflection at joint C, I will apply a unit load at joint E by removing all the external loads that are provided in the section. Okay, so your step 2 is you have to remove all the external forces and apply a unit load under what situation you are expected to calculate the deflection. So that will become your capital N. Okay, now after that you have to calculate, you after applying your unknown, that is after applying your unit load N. Oh no, after applying unit load, you will calculate all the values of capital N. Then what you will do, you will calculate all the internal forces in the trusses using unit load concept, and that will give you the value of small n. After that, you will utilize the principle of virtual work, in which the deflection is calculated by the formula given to you in the highlighted box. Okay, so this formula is derived based upon the principle of virtual work concept. So let's see one problem related to this, then it will clear all your concepts. So in this, you are expected the member forces in the truss are given to you. So what are the forces in the members? So now first you will calculate all the forces. So how you will calculate all the forces? Basic concept. First calculate all the reactions. So we are calculating 4 reactions in this case: VD, HD, VC, HC. But you have only provided with the 3 equations. Okay, so if you apply that, you will get to know the value of horizontal reaction VD to be equal to 60 kilonewton. And when you apply summation of moment about point A, from that you will get to know the value of VC plus VD to be equal to 0. Now you are not getting all the 4 unknowns in the equation. So what you will do, we will start with one joint, that is your D joint. So if you apply the method of joints at D, when you draw the bending moment diagram, from that you will came to know that your VD is coming out to be 0. So when your VD is 0, that means your VC is 50 kilonewton. Okay. Now we will proceed to calculate all the member forces in the section. Okay. So using method of joints. So we will apply the method of joint at joint C and then calculate the unknown member forces, that is your member CB and your member CE. After that, we will move to joint P and we will determine the value of unknowns at that, where your unknowns are BE and your unknowns are BA. Okay. Then we will move to joint A and then we will calculate the rest of the unknowns that is there in the truss. Now after that, the question is asking you to calculate the vertical displacement at joint A. So as we have read in the concept, that if you require to calculate the deflection at particular point, what you need to do, you need to apply the unit load in that particular direction. So in this case, we are expecting to calculate the vertical deflection at joint A. So we will apply downward low unit load in that particular point, that is point A, and then we will analyze the truss in same way that we have analyzed previously. We will use method of joints and then determine all the member forces, that is AB, AE, ED, BC and BE. So after determining all the unknown forces, in the question, what we will do, we will solve and get to know the value of vertical displacement. So to get to know about all of these, we will make one table. This table will give you an overview to analyze and get to know the deflection value. First, we will write all the member forces. So we have 6 members in this truss. We have written all the values of capital N that we have determined from the external forces. Then after that, we have removed all the external forces and apply a unit load in the vertical direction at point A. Then due to that vertical load, what are the forces you are expecting or you got in the member forces? We have written in small n column. In capital L column, we have written all the lengths of the different member, and then we have determined multiplication of small n, capital N, and into L. Okay. Then we will do the summation of capital N, small n, and L. From that, if we divide that with the axial rigidity, that is AE, you will get to know the value of deflection at A in the vertical direction. And it is coming out to be positive. So your deflection is in downward direction and it is equal to 6.2266 mm. Okay, so this is how you will use to solve the problem related to principle of virtual work in trusses. Now we will analyze beams and frames for analysis of statically determinate structures. So first method that is available for you is the moment area method. So now what is moment area method? So in moment area method, you have the two theorems, that is the deviation of a point relative to the tangent drawn to the elastic curve at any point in the direction perpendicular to the original position of the beam is equal to the moment with respect to B of the area of the bending moment between A and B divided by EI. So when you are calculating area of the bending moment diagram, then you will get to know only the slope. But when you are calculating moment of the area of the bending moment diagram between two particular points, then it will give you the deflection at that particular point. So this is what moment area method tells to you. Okay, so you have some standard results available to for you. This you can also one have each and every one every result you can derive using moment area method, or you can say some other method, or you can say we have one more method. We can from that also we can calculate, or I think conjugate beam method. From that also you can calculate. Okay, so using the standard results, we have the standard result for cantilever beam subjected to a point load at the free end. So when you did that, you will get the maximum deflection at the free end to be equal to minus PL cube upon 3EI. You can write whatever sign depending upon your sign convention. And the maximum slope in this case is coming out to be PL square upon 2EI. Similarly, for different loadings, we have different formulas available. So you can use any one of the formulas and then get to know the value of deflection at that deflection and the slope at that particular point. Okay, so let's solve some one problem related to that. So in the question, it is given to you, in case of simply supported beam AB, theta AP is the theta AP is the slope at the point support A if concentrated load is applied at a midpoint. Now, if the load of the same value is equally distributed all over the beam, then what will then the we get the slope as theta AU. So okay, in that case we are expressing the slope to be equal to theta AU. Now you are expecting to calculate the relationship between theta AP and theta AU. So as drawn in the diagram for the case 1, we can say a point load is applied at the middle of the beam and the slope that is expected in this case is coming out to be theta AP. Whereas in case 2, you are seeing the W load is applied, which is equal to capital P upon length. In such situation, the slope you will be experiencing, it will be equal to theta AU. Okay. Now you have to define the relationship between theta AP and theta AU. So for the first case, if you define theta AP, it will come out to be equal to PL square upon 16 EI. Whereas in case of theta AU, it will come out to be WL cube upon 24 EI. Okay. Now what you will do, you have to define the theta AP. Okay. So first we will see how this PL cube upon 16 AI came. Okay. So what we will do, we will draw the bending moment diagram for this case. So between point A till the middle of the beam, you will calculate the area. That area will come out to be equal to 1 by 2 into PL upon 4 EI multiplied by the half length of the beam, L by 2 divided by EI. So if you do that, you will get to know the value of slope to be equal to PL square upon 16 EI. If you further take the moment of this area of the bending moment diagram, you will get to know the deflection also. But in this case, we are not required, so we have only calculated the slope of AP. Now, on the same lines, if we calculate the slope of the we can say uniformly distributed beam, under such situation, you got to know the value of theta AU equal to WL cube upon 24 EI. And when you compare both the values, okay, and you will simplify them further, you will get to know the theta AP upon theta AU to be equal to 3 by 2, or you can say equal to 1.5. Okay. Now let's see, we are expecting to solve one more question. In that question, it is given to you, you have uniformly varying load all over the beam section. Now you are expecting to calculate the deflection at point B. So first what we will do, we will divide the whole beam into two parts using principle of superposition. One part will be your constant load, that is you can say uniformly distributed load all over the section, and another part will have uniformly varying load distributed all along the section. Now when you will determine the moment xx, it will be equal to wh square upon 2, and it will be equal to wh cube upon 6l for uniformly varying load. Now for the complete length L, if you determine that, you will get to know the maximum value to be equal to 125 upon EI for uniformly distributed load. And for uniformly varying load, since that will be a 3-degree curve, you will get to know the value equal to 125 upon 6 EI. Now you are expecting to calculate theta B, and theta B you are calculating with respect to A. So at point A, your theta A is 0. So that means your bending moment area of the bending moment diagram between A and B divided by EI will give you the slope of B with respect to A. Okay, that you can divide it further to be equal to area with respect to UDL plus area with respect to uniformly varying load. Now, if we calculate the area of both uniformly distributed load and uniformly varying load, and when we sum up them, we will get to know the value of slope at that particular point, that is point B. And in such case, we will get to know the value to be equal to minus 3125 divided by 24 EI. Furthermore, if we calculate the deflection values, okay, in that case, we need to calculate moment of the area of the bending moment, not only the bending moment diagram. We need to calculate moment of the bending moment diagram, and then we did that same. In same case, we will take for both the section for UDL as well as for UVL. Then we add them. We'll get to know the value of deflection. Okay. So this is how you use to calculate for beams and frames using moment area method. As I already told you, we have one more method available, that is conjugate beam method. So let's see how you will use that conjugate beam method to determine the deflection for beams and frames. So we have five steps available to determine the slope and deflection in case of conjugate beam method. So what you will do, you will first draw the bending moment diagram of the real beam. Okay. Then you will convert the bending moment diagram into M upon EI diagram as same as you used to do for the moment area method. Now what we will do from this step? From this step, we will calculate the real beam. We will convert the real beam into a conjugate beam. So how we will do that? We will make the hinge support to be a roller support to be a hinge support. In case of fixed support, it will become free support. In case of free support, it will become fixed support. So there are some conventions that you are expected to use when you are changing, or you can say converting a real beam into a conjugate beam. Okay. After that, whatever shear you are getting from shear and bending moment you are getting in case of the conjugate beam, that shear will become slope of the real beam, whereas the bending moment diagram of the conjugate beam will become the deflection of the real beam. So this is the basic principle for the conjugate beam method, wherein the shear of the conjugate beam will become the slope of the real beam, and the bending moment diagram of the conjugate beam will become the deflection of the real beam. So, in this regard, we have one problem to solve. So, if you see this problem, you are having one internal hinge, and this is a prop cantilever subjected to a load of 25 kilonewton uh, at the middle of the span BD. Under such situation, what you will do? You have one more equation that due to internal hinge that will give you the value of capital dy, or you can say reaction vertical reaction at point D. Using that, if you calculate another reaction, that is value of by, it will give you the same value equal to 12.5 kilonewton. Now for span AB, the value will come out to be equal to 12.5 kilonewton. Now since the point A is a fixed support, so a moment will also come at point A. So if you calculate the moment about point A, it will come out to be equal to 37.5 kilonewton meter. Now draw the free body diagram of the real beam that is given to you. Mention all the unknowns that you have calculated using equilibrium equations. Okay, that will give you a depiction of the real beam. Now what you will do, you will convert this real beam into conjugate beam based upon the bending moment diagram of the real beam. That will become loading for the conjugate beam. So whatever the bending moment diagram we are expecting in this case, it has become the loading for the real beam, and rest are the convention for the support, wherein we have already told that roller support will become hinge support, fixed support will become free support, and internal hinge will become roller support. Okay, so applying all the conventions and then further calculating first their unknowns, that is their reaction values. And after calculating the reaction value, if you calculate the deflection at point C, what you will do, you will take moment about point C. Okay, so for this case, moment about point C, it will be equal to the slow deflection at point C, and it is coming out to be equal to 168 upon 5, 168.5 divided by EI. Okay, similarly shear at point C will be determined based upon the it will give you the slope at point C of the real beam. So shear force at point C dash of the conjugate beam will become equal to the slope of the real beam, and that will give you the value of slope to be equal to 18.75 divided by EI. Okay, this have covered all the concepts related to statically determinate structures for trusses, beams, and frames. Okay, so all the methods that are required for them we have currently discussed. Now we will go to influence line diagram where we can see how Mueller-Brislow law principle can be applied. So, what does Mueller-Brislow law principle tells to you? It says that the influence line for any force response function in a structure is given by the deflection shape and the structure resulting from a unit load or rotation corresponding to the force and the moment under consideration. So another step is what is the significance of this principle? That is, it is used for studying of the moving load on the structure as a part of influence line diagram. Then it will also help in finding out the live load location to get the maximum stress value in the member. After that, it will also help in finding out any stress function under critical value. Okay, so all these are the concept for the Mueller-Brislow principle. So this principle in static analysis will be applicable for both determinate as well as indeterminate structures. Okay, so let's see few problems related to that. So in this, a beam is given to you of length 9 meter. No external load is applied, and you are expected to draw the influence line diagram shape for the shear force about point A. So now you are expected to calculate the shear force about point A. Then how the influence line diagram will look like. So what you will do, you will take a unit load that is kept between A and C, and then you will determine all the unknowns. So first, if you calculate all the unknowns, that will come out to be equal to 23. Sorry, it will come out to be equal to, when you kept unit load between A and C. After keeping that, you can calculate reaction force RA and RB. Since both are unknown, we will use third equation of equilibrium equation. That is the moment about point A to be equal to 0, and that will give you the value of reaction A to be equal to 1 minus x upon A. Okay. So in this case, when x is equal to 0, your RA will be equal to 1. And if your RA is equal to 1, that means your shear force at A will become equal to 0. Now, when your x is at 3, so under such situation, your RA will become 1 minus 3 upon NA to be equal to 2 by 3. Okay. And when you calculate shear force at A, it will become equal to 2 by 3 minus 1 equal to minus 1 by 3. Okay. Further, when you have unit load to be kept between B and C, under such situation, the we will calculate the reactions first, and then we will calculate shear force at C. Okay, after calculating shear force at C from both the location, we will get to know the value of shear force, or you can say bending moment diagram. So in that situation, or you can say in current situation, it is coming out to be a triangular figure where the load is expected. Okay, so that is how you will use the concept for influence line diagram. Another question is, when you have a uniformly distributed load moving throughout the section, which has the length very less compared to the length of the beam. Under such situation, it is telling you to calculate the absolute bending moment at point C. Okay, so to get to know the maximum bending moment about point C, the load should be kept at C in such a ratio that it will divide the beam and the load in the same ratio. So it should divide the beam and the load in the same ratio. Okay. Now, when you check the distribution on the left hand side, it will come out to be equal to 2 into 3.9. Okay. If you determine the load distribution from the left side, it is coming out to be equal to 0.67, whereas from right side it is coming out to be equal to 0.133. Okay. Now, what is expected further? is to determine the value of x. So how you will determine the value of x? It is depending upon the equilibrium equation as well as the property of triangles. From that, we will get to know the value of x to be equal to 1.557. On the same lines, if you calculate the value of y, it will come out to be equal to 1.553. Now, after determining all the values, we can calculate the maximum bending moment at C. And if you do that, what do you have to do? You have to calculate all the area of the bending moment diagram. Okay. And then if when you multiply it by 1 upon EI, it will give you the value of, or you can say it will give you the maximum bending moment at that particular point. Okay. So now till this point, we have covered analysis of statically determinate structures. Now we will solve the problems related to indeterminate structures. So for indeterminate structure, the basic concept you have to see is what is the degree of static indeterminacy. If the degree of static indeterminacy is coming out to be equal to 0, your structure is uh, your structure is statically your structure is statically determinate. Whereas when the degree of static indeterminacy is coming out to be more than 0, then your structure is statically indeterminate. Okay. So for that we have two, we can say method. One is force method, another is stiffness method. So force method is also known as flexibility method, whereas the stiffness method is known to be displacement methods. Okay. So there are infinite many systems which satisfy your equilibrium equation. But among all, there is only one system that will satisfy the boundary equations. So to get to know about that, we require additional equation to solve the system. So how we get to know that equations to solve the system? That is using force and displacement method. So further, how we'll calculate the problems using force method. So in this force method, we used to take the redundant forces at unknowns, and then we will determine the additional equations. As we have the degree of static indeterminacy, so we require some additional equations to solve the problem. So how this additional equation can be obtained? So these additional equations are obtained to solve the displacement compatibility. So what are the steps that are required to solve for the force method? So first step, determine the degree of static indeterminacy. After that, select any force or any moment which will be your redundant. Okay. Then remove that force and then solve the structure based upon the basic redundant structure under the load that is provided to you. Okay. Now after that, solution is determined for the redundant force only by removing all the external force. Now what you will do, you will remove all the external forces and then apply the redundant force and then see what are the values that you are obtaining for different members, and then you will apply the compatibility equation at the at the end which you are expecting. Generally we will apply the compatibility equation based upon the reaction support. Like you say, if you take one fifth support, in the fifth support your deflection is 0 and slope is also 0, so that can become your one of the compatibility equation. So if you use that equation and then solve the problem, then you will be able to solve using that force method. And then after that we will use and solve for other unknowns. Now what is the basic difference between the flexibility matrix or the force matrix and the displacement matrix or the stiffness matrix, or you can say method? In force method, I will again explain the procedure, and similarly I will again explain the procedure for the stiffness method. And Comparing the method of solving the both the methods, you will came to know what is the difference between force and stiffness method in your solution purpose. Otherwise, there are many differences in them. Okay. So first method. First step is to determine static indeterminacy. After that, determine redundant forces, and then find the displacement in basic statically determinate structure under load and redundant forces. Both. This is a two-step point. The point number three is a two-step point. First, you determine under basic load, and then after that, you will again determine under redundant forces. Then express the displacement in terms of redundant using flexibility format. And finally, you will be able to solve the compatibility equation and find the unknown redundants. Okay. Then you will see how the unknown can be determined. Whereas in case of displacement method, or you can say stiffness method, you will not determine the static indeterminacy. You will determine the degree of kinematic indeterminacy. So then you will identify unknown displacement whose number will be equal to nk, or you can say n under root n, so subscript k. Then restrain the above displacement and find forces in the basic kinematically determinate structure, and then you will express the forces in terms of displacement using stiffness format and solve the equilibrium equation to find the unknown displacement. So this is the basic points that you will, or you can say algorithm to solve both the methods. We will solve each one problem for each method, and then you will be able to see how you can use both of these methods. So your first problem is, for this case, that in the following statically indeterminate beam. So in the question it is already given that it is indeterminate. If you want to calculate the indeterminacy, in this case your indeterminacy will come out to be equal to 1. Now consider the vertical reaction at point C as a redundant force. Then calculate the vertical displacement at point C, and that will express as d1 for the beam with the point load without any restraint at C. Then determine the value of d1. Okay. So using force method, how you will do? First, take the degree of static indeterminacy. So in this case, your number of unknowns are 4, 3 because of that you can say fit support, and 1 because of the roller. So in this here it is not hinge, it is fit support. Okay. So this is your fit support, and another one is your roller, which will give you the one unknown reaction. When you subtract them from the available equilibrium equation, you will get to know the value of degree of static indeterminacy to be equal to 1. Now you have to choose one reaction as redundant and then remove them and further calculate the basic displacement under the loading condition. So what we will do, see in this diagram, we have removed the reaction at C, and now we will determine the, you can, what you can say, we will determine the displacement at point C. So how we can determine the displacement at point C? We have two methods available. Either you can use moment area method, or you can use another method which is conjugate beam method. So for the current problem, we are using the conjugate beam method, in which free end becomes the fixed end and your fixed end become the free end, and your loading, your bending moment diagram will become the loading for the conjugate beam. Okay. After using all the concept for the bending moment, so this will become your conjugate beam. So this is your conjugate beam, and the above one is your real beam. Okay. Now what you will do to determine the displacement at the point C, you will determine the moment of the bending moment diagram between A and B, or this is not a moment area method. This is a conjugate beam method. So in this case, the moment that will come out at point C will become the deflection for the real beam. So what we will do, we will calculate the moment about point C, and that will give you the deflection at the free end. So how we will determine? We have taken all the loads multiplied by their corresponding moment, and from that we will get to know the value equal to 3125 upon 3 EI. That will become the deflection at the point C. Okay, when the corresponding prop support is removed. Now, what we will do? We will apply a unit load at point C. Okay, because we are now using the uh, force method, or you can say flexibility method, to solve the problem. Now, using force method, either you use your direct value of the standard from the standard result, or another is you can use moment area method or the conjugate beam method. So again we are using the conjugate beam method, and then we have determined the moment at support C or moment at point C, and that will give you the deflection at the free end at the free beam of the real beam. And in this case, if you determine the deflection, it will come out equal to minus 1000 Cy upon 3 EI. Okay. So now you got two displacement, deflect, or you can say deflection, D1 and D2. But if you see, you have the support that is provided to you at end C, and due to that support, the vertical displacement will should be equal to zero. That will become your compatibility equation. So that is why your D1 plus D2 in this case will become equal to 0. And when you simplify this equation further by substituting the value of D1 and D2, you will get to know the value of unknown, that is your reaction Cy, and its value will come out to be equal to 3.125 units. Okay, so this is how you will use the force method to calculate the unknowns in case of beams. Now, how we will solve in case of trusses? So for trusses, we will use method of consistent deformations. So method of consistent deformation is also known as force method. So it is based upon equilibrium equation as well as the compatibility equation that we generally use for the force method. It determines unknowns in statically indeterminate structures, and the method formulates a set of compatibility equations depending upon the number of redundant forces. So this is the same force method that we have discussed previously. Now, what is the procedure to solve for the truss? First, determine the degree of static indeterminacy. So for truss, how will determine the static indeterminacy? It will be equal to m plus r minus 2j. Now, whatever the value of static indeterminacy you will came to know, you will remove the exact number of redundant forces or moment from the structure. After removing all the redundant forces, you will determine the solution of the determinate structure under the given load. Okay. After determining their solution, now you will remove all the external forces and you will now apply the redundant forces. Now, due to these redundant forces, what are the values you are expecting in the force members that you will determine? Okay. Then you will calculate the deflection for the determinate structure and the structure with the redundant force. Okay. Then we will use compatibility equation, and that will help you in solving the unknown values. Okay. So this is one question. So I am taking one big question in this case, because if you take the big question, that will if we solve step by step, that will clear all your concept. Otherwise, I could have taken 1 degree static indeterminacy case also, and that will clear your concept. But for your purpose, what happens when the degree of static indeterminacy will come out to be equal to 2? Then how you will solve that? Okay. So let's see this question. In this, you have to calculate first the degree of static indeterminacy. So if you solve the degree of static indeterminacy, it will come out to be equal to 2. That means your structure is indeterminate of second order. Okay. Now, what is given to you in the question? You have to solve the problem using method of consistent deformation using the equation. So this equation is based upon the method of consistent deformation as you have solved previously. So for our problem given in the question, the DL1 and DL2 are assumed to be displacement along the members BD and the horizontal reaction B. So why we have taken the horizontal support reaction and one member? Because one is having an external indeterminacy and one is having the internal determinacy. So when you have one external indeterminacy, you have to take one redundant force as an external member and one as an internal member. When your external indeterminacy is zero, then you can take both the member as the internal redundant member and then remove them and then solve the problem. But in this case, one member is externally redundant and one is internally redundant. So for the first case, we will remove the horizontal reaction from B. So if we remove the horizontal reaction from B, that will become a roller support. Okay, so in this, your member force BD will become your redundant force as a second redundant force. Now consider this after removing both the redundant forces. So we have removed both the redundant forces. One is the BD member and another is the horizontal reaction at point B. Now we will analyze the structure. First, we will determine the reaction unknowns. So that will give you the corresponding values to be equal to RB will be equal to 0 and RA will come out to be equal to 10. Okay. Now we will remove all the zero force members in the structure and then determine the value of the member forces. Okay. So this is the diagram that is depicting you all the member forces, wherein AC is having a 100 kilonewton in tension and AD is having the 50 kilonewton in compression, whereas rest all members is having zero force. Now, what we will do, we will apply the redundant force and then see what is the value that is coming in the member forces due to that. So first, we will take the case of BD, where we have removed the diagonal force BD. So we will apply unit load in both the direction, and then due to that, in the all the members, what are the reactions that what are the forces that are coming? So for AD and BE, you are getting zero point 0.6 as the in compressive direction, and for AB and CD, you are getting zero point 0.8 as the compression of member compression force. Whereas when you apply 1 kilonewton due to the horizontal reaction force, which is taken as redundant, you will get only 1 kilonewton equal to in tension, whereas all the members will be in the zero force members. Okay. Now we have made one table. First, write all the length of the members. Then you write Ni, which will give you the values of forces in the member after removing the redundant forces due to the application of external forces. Now, N1I will give you the value of forces in the member due to redundant force BD, and N2I will give you the value of member forces due to the application of redundant force at support B. Okay, so if we solve them, we will first determine all the flexibility coefficients. Okay, so we got the flexibility coefficients using the formulas provided to you. So here F11 came out as 34.56 upon AE. F22 came as 8 upon AE. F12 and F21 came equal to minus 6.4 divided by AE. So from this we got to know our flexibility matrix. Now we also require our D1 and L and D2L. So for D1L and D2L, we have the formulas for the using method of consistent deformation. From that, we got to know the D1L will come out to be equal to 1180 divided by AE, and your D2L is equal to 0. Okay. Now, when you substitute all the values that is provided to you in the quotient, okay, or you can say compatibility equation, you will get to know the value of unknowns. So your unknown in this case is h1 and h2. If you substitute them, you will get to know the values equal to minus 40.08 and minus 32.07. Now if you are expected to calculate any forces, like you are expected to calculate force BD, what you will do, you will use the formula uh, for the corresponding member, and then you will get to know the value of corresponding force. Okay, this is how we will solve the problems for the trusses. Now let's see two concepts for uh, dif- uh, two methods for the displacement method, or you can say stiffness method. One is slope deflection method and another is moment distribution method. So for the slope deflection method, how we will use that? So let's see, we have a portal frame given to you. Okay, in this case, we can make the BD member to be equal to a concentrated moment that is applied at the point B in the anti-clockwise direction, and that will give you a two span member where AB is having the length of 4 meter and BC is having the length of 6 meter. Further, you can use the compatibility equation. So in this, you can use the compatibility equation at joint B. That is your M moment at point B due to D. That is MBD plus MBC plus MBA will be equal to 0. Now, what we will do? We will determine the moment of all the members forces at that particular point. Okay. First, MBD we will calculate. That will give you equal to 40 kilonewton meter. Then we will calculate MBC. How we will use? How we will calculate? We will use slope deflection method. So for using slope deflection method, we already know that MBC is equal to sum of fixed end moment of in member MBC, that is MBC bar, plus 4EI upon LBC into theta B plus 2EI upon LBC into theta C. In this case, your theta C is equal to 0 because of the fixed support that is provided to you. So further, all the components will be calculated. So your MBC, as you have the loading to be uniformly distributed load, so your MBC will come out to be minus WL square upon 12. If you substitute all the values, you will get to know the value equal to minus 24 kilonewton meter. Then when you substitute the values, all the values, you will get to know the value of MBC to be equal to minus 24 plus 2 by 3 upon EI into theta B. So here your theta B is your unknown that you will calculate when you use the compatibility equation. Now, if we take the span BA, so for span BA, same, we will apply the you can say slope deflection equation. So if you apply the same slope deflection equation, since there is no load over that span, so your MBA bar will become equal to 0. Further, your theta A will also become equal to 0 because you have fixed support provided at theta A. And then you will be only remaining with MBA equal to 4EI upon LBA into theta B. Okay, that will give you the value equal to EI up into theta B. Now substitute all the values that you have got for MBA, MBC, MBD equal to 0. Okay, if you do that, you will get to know the value of EI theta B to be equal to minus 9.6 kilonewton meter square into radian. Okay. After that, if you are expected to calculate MBA, you can calculate it to be equal to minus 9.6 kilonewton meter, and further all other values can be calculated like MAB to be equal to minus 4.8 kilonewton meter. Now, if you draw the free body diagram, you can further calculate the horizontal support in the structure, that is your HA. How we did that? We have drawn the free body diagram of member AB, wherein at B you are getting a anti-clockwise moment of 9.6 kilonewton meter, and at A you are getting an anti-clockwise moment equal to 4.6 kilonewton meter. After that, if you apply summation of moment at B to be equal to 0, then you will get the value of horizontal reaction at A to be equal to 3.6 kilonewton meter. Another concept to solve for beams and frames is using moment distribution method. So moment distribution method is also one of the displacement method. This is used when you have large frames Okay, under such situation, what we will do? We will use moment distribution method. So, what is moment distribution method? It is the distribution. So, that means you have to first calculate the distribution factors. So, first of all, we have to know what is the stiffness at that particular point. Based upon the stiffness at that particular point, we will determine the distribution factors. Okay, so in this case, you are provided with a continuous beam which is having a support, fixed support at end A, and at B and C it is having a roller support. Okay, then you will calculate the stiffness at due to BA and stiffness due to BC. Since your end support, or you can say far end at in BA is fixed support, that will give you the stiffness to be equal to 4EI upon LAB. And when your far end is hinge support, you will get the value as 3EI upon LBC. Substituting the values, you will get to know the value of KBA equal to 4 upon 5 EI, whereas KBC will come out to be equal to 6 upon 5 EI. Now, distribution factor will be depending upon the uh, value of BA at that particular point divided by the total distribution factor. And if you do that, you will get to know for the case of BA, it will come out as zero point 0.4, and for BC, it will come out as zero point 0.6. Okay. Now, in the next step, you will calculate the fixed end moments. So, if you calculate the fixed end moments, you will get to know the values of MBA and MAB equal to minus 25 kilonewton per meter for MAB, and for MBA it is coming out to be 25 kilonewton meter. Whereas for the BC span, there is no loading, so their fixed end moments will become equal to 0. Now we will start using moment distribution method. First, we will write all the joint, then we will write all the member forces, and then we will write their corresponding distribution factors. So after writing all the distribution factors, we will write their corresponding fixed end moments. Okay. Now in this case, you can see at joint B, you are getting a not equal distribution of the fixed end moment in BA and BC. Then what you will do? You will divide this in on the basis of their distribution factors. So 25 is divided into minus 10 in minus 15 based upon their distribution factors, and their carryover and their corresponding carryover moment will be provided at span A and span C. That will give us the value, cumulative value equal to minus 5 plus 15 minus 15 and minus 7.5. Again, you have the you can say hinge support, or you can say roller support at A. So no moment will come at C. So what you will do? You will apply the reverse moment at that particular direction. So what we will do? We will apply for minus 7.5. We will apply plus 7.5 in that, and due to that plus 7.5, carryover moment of 3.75 will come into picture, and due to that your final end moment will become minus 30 plus 11.5 minus 11.25 and 0. Now still you are having 4.75, not 3.75 as the unbalanced moment at joint B. So this 3.75 is divided based upon the distribution factor again into minus 1.5 and minus 2.25, and their corresponding carryover moment is provided at joint A and joint C. Again, at joint C, moment should be equal to 0, so plus 1.13 is provided as 0.57 as the distribution factor. And now this 0.357 will become equal to minus 0.34 and 0.23 based upon the distribution factor. And their further carryover moment will give you the final end moments to be equal to minus 30.87, minus 13.27, and plus 13.27, and 0 at end C. So this will give you the value of moment at different points using moment distribution method. Okay, so this is how we use to solve the problems for these cases. Okay, now what we by this 11th week we have covered all the concepts related to analysis of statically determinate beams as well as analysis of statically determinate analysis of statically indeterminate beams, frames, and trusses. Now we are introducing to you one more concept, that is matrix method for both, or you can say stiffness. For currently we are only providing for the stiffness method, but there is one more method, that is flexibility matrix method. We are not touching that. We are only touching the stiffness matrix method. Okay, that will give you a glimpse of the part 2 of the statically and static analysis course. Okay, that how you will solve the problem in the advanced course. Okay, so for the direct stiffness method, first I will discuss some of the properties related to the stiffness matrix. So this stiffness matrix is a square and a symmetric matrix which is related to forces and displacement, in which all the diagonal elements are always positive and the sum of elements in any column will be equal to 0. Now it is having different properties. First is it is square and symmetric. Second is it is having positive diagonal elements. Third is sum of elements in any column is equal to 0. Fourth is the size of the matrix will depend upon the number of degrees of freedom of the structure. Okay, and then stiffness matrix is the inverse of the flexibility matrix, and the stiffness matrix can be developed when the structure is stable. Finally, these stiffness matrices are singular, that means their determinant is 0 and the matrix cannot be inverted. Okay, so these are few, you can say, properties related to stiffness matrix that you should check whenever you are making any stiffness matrix. So let's see how we will define a stiffness matrix. So in this case, you are given a truss. Now, it is not asking you to directly determine the stiffness matrix. It is asking you just to give what will be the global dimension of the, or what is the dimension of the stiffness matrix. So how we have, so as per the stiffness matrix properties, the size of the stiffness matrix, or you can say the dimension of the stiffness matrix, will depend upon the degree of the kinematic indeterminacy, or you can say degree of freedom of that particular structure. So in this case, at joint A, you are having 2 degrees of freedom. One is horizontal direction and vertical direction. And at each and every joint, that is at joint B and joint C, you are having two degrees of freedom. Okay, so when you accumulate all of them, you will get the degree of kinematic indeterminacy to be equal to 6. Okay, so that will become your size of the stiffness matrix equal to 6 by 6. Now another question that is provided to you is to determine the flexibility matrix. So how we determine the flexibility matrix from stiffness matrix? We have again provided an property, that is the flexibility matrix is the inverse of the stiffness matrix. So what we will do? We will take the inverse of the stiffness matrix, that will give you the flexibility matrix. So what is the formula, or you can say how you determine the flexibility matrix? It is 1 upon determinant of the stiffness matrix multiplied by the transpose of the adjoint of the stiffness matrix. So let's see. First we will determine the stiffness matrix, and after determining the determinant of the stiffness matrix, it is coming out to be equal to minus 8EA. Then to determine the adjoint of the stiffness matrix, first we have to calculate the cofactors of stiffness matrix. So if we calculate the cofactors of stiffness matrix, it is coming out to be is to be equal to 2 minus 4 minus 3 and 2 correspondingly, I can say respectively. Then adjoint of stiffness matrix will be equal to the cofactor of the stiffness matrix, transpose of the cofactor of the transpose of the cofactor of the stiffness matrix, and that will become equal to 2 minus 3, 4 and 2. When you multiply 1 upon determinant of k into adjoint of k, that will give you the flexibility matrix. Okay, so this is how you will determine the flexibility matrix from the stiffness matrix. So till now we have solved few problems related to the application of the properties of stiffness matrix. Now the third case, or you can say another question that is provided to you, is the you have to determine the stiffness matrix of the following beam. So in this case, if you have to determine the stiffness matrix of the following beam, what you will need to do, the size of the stiffness matrix depend upon the number of degrees of freedom of that particular structure. So in this case, when you neglect the axial deformations, only 2 degree of flexibility, you can say degree of freedom will come into picture. One is your vertical degree of freedom and one is your moment degree of freedom. Okay, so your 2 by 2 matrix of the flexibility, 2 by 2 flexibility matrix can be calculated using the following concepts. So your K11 will be the displacement at point A when you are providing a unit displacement at point B, or sorry, displacement at point B when you apply a unit rotation at point B, or sorry, unit displacement at point B. So when you provide a unit displacement at point B, due to that, moment will come into picture. Because of the application of moment, the unit displacement will come. So as you already know, so for that case, the moment application should be equal to EI upon L square. Okay, so to compensate that, you have to apply the shear forces, and that shear force will become EI upon L cube. So your K11 will become 12 EI upon L cube. Now your second K12, it is due to the application of unit displacement at point B, what is the amount of rotation that you are expecting? So you are expecting the rotation to be equal to 6 EI upon L square. So that will become your K12. Now the next step is when you will apply a unit rotation at A, then what are the moments and reaction you are expecting? So when you apply a unit rotation at point A, so then correspondingly your moment at point A B will become equal to 4 EI upon N, and your moment at A will become equal to 2 EI upon L. So to make the structure stable, an anti-clockwise couple is provided with value equal to 6 EI upon L square, and that will give you two components of the stiffness matrix K21 and K22 equal to minus 6 EI upon L square and 4 EI upon L. Okay, now this will give you a stiffness matrix. Okay, in this case you can see that this stiffness matrix is a square matrix and it is also symmetric. That means when you transpose this matrix, you will get the same matrix again. Okay, this is how you will determine the stiffness matrix, and this will complete your course regarding the structural analysis. So I thank you all for being patient with me during all the lectures that you have covered till now, including this present session. Okay, so again I will recap you. I used to recap each and every topic or you can say every concept that I used to cover in the class at the end, so that you will get to know after the end of every session that what you have learned from that particular session. But today's session is big. It is regarding the summary of the whole course. It is regarding you providing of image of what you have learned in this current course. It is this session you can also say is the revision of your complete structure analysis course, and this can also helps you in getting to know that what are the concepts that are required to analyze any structure or frame. It could be either frame, it could be either beam, or it could be either truss. So let's revise it, or let uh, hear what I am telling you in brief about what you have covered in this structure analysis course. So we started with analysis of beams. So first we have revised our concepts using defining the shear force diagram and the bending moment diagram for different loading conditions. So we have seen under what conditions you are expecting 2 degree bending moment diagram, under what condition you are expecting linear bending moment diagram or 1 degree by bending moment diagram, and under what conditions you are expecting constant bending moment diagram, or you can say due to constant moment applied at particular point. Okay, so that we have seen in the week one. After that, we have seen about the trusses. So we have seen how you will analyze the trusses. That means you have to determine the forces in the member of the trusses using two methods. We have method of joint and in the method of section. And as I already told you, when your structure is very complex, you will use method of section to determine only when you are expecting to calculate one or two member forces at that particular joint. Okay. But when you are expecting to calculate all the member forces, use method of section, or sorry, method of joint, because that is easy for you. You just have to apply the equilibrium equation and then get to know the value of forces. In the third week, we have seen how we can use the principle of virtual work and get to know the value of deflection. It could be either horizontal deflection or the vertical deflection in the trusses using the principle of virtual work. They have defined one formula, that is delta is equal to capital N into small n into L divided by axial rigidity, that is AE. After that, we have moved to the week 4. In week 4, we have analyzed beams and frames, and in that, we have seen how you can apply moment distribution moment area method. So first method we have seen is moment area method. So in the moment area method, two theorems are there. One is the area of the bending moment between 2 points will give you the corresponding slope of that point with respect to another point. Whereas the moment of the area of the bending moment diagram between the 2 points will give you the deflection at that particular point with respect to, or you can say in relative to, the another point. Okay, so based upon these two theorems, you use the moment area method and get to know the value of slope and deflection for beams and frames. Another method we have utilized is the conjugate beam method. So in conjugate beam method, what you used to do, you used to convert your real beam into the conjugate beam. So how you used to convert your, in this you have some basic convention wherein hinge support will remain hinge support, your roller support will become internal hinge support, and your internal hinge support will become your roller support. Your fixed support will become your free support, and your free support will become fixed support. And then your bending moment diagram will become the loading diagram for the conjugate beam. And after that, when you will calculate the share of that particular bending moment, share of that particular conjugate beam, you will get to know the value of slope at that particular point. And when you will calculate the bending moment of the conjugate beam, that will become the deflection of in the real beam. Okay, so these are the two basic things that you will use in conjugate beam method. After that, we have used the we have seen the concept related to the influence line diagram, wherein the moving load, when it moves over the structure, how you can determine the maximum reaction force and maximum bending moment based upon the proportion of the loading that is divided over the section. We have seen that. Then we have introduced to you for the analysis of the statically indeterminate structure, wherein we have seen two methods are given to you. One is the force method and another is the stiffness method. So in the force method, what you have to do, you have to use the method of consistent deformations. So what is that? You have to first calculate the degree of static indeterminacy. Then the number of depending upon the degree of static indeterminacy, you will remove the number of unknowns, and after that, removing the unknowns, you will analyze the structure under the given loading conditions. After that, you will remove all the external loads and then provide the redundant forces to the structure, and then again calculate the for member forces, or you can say the displacement, whatever compatibility based upon the compatibility equation that is derived. So then you will apply the compatibility equation and then solve the problem. Whereas in case of displacement method, we have two displacement method. One is slope deflection method and another is moment distribution method. So in slope deflection method, we have the given formula. Using that given formula and the compatibility equation, you can determine the moments at all the points of the section. And further, if you are expecting to calculate shear, then you can use the free body diagram of that particular span, and then you can calculate the value of horizontal forces, vertical forces that are coming out over that particular section. Then we have used the moment distribution method. So moment distribution method is based upon the distribution factor. So how you will calculate distribution factor? Distribution factor is first we will calculate all the stiffness at that particular joint using far end condition. So based upon the far end condition, you will calculate the stiffness at that particular joint, and then you will distribute based upon their values. Okay, based upon their values and divided upon the sum of the total stiffness that is coming over the section. Okay. So after doing that, you will use the moment distribution method. How you will do? You whatever undisturbing moment that is coming out in the particular joint, you will divide that in terms of the distribution factors. After dividing them in terms of distribution factor, you will provide the carryover moment to the remaining joints. Then you will again check that whether any undisturbed moment is available in that particular joint. If so, then you repeat that step till your undisturbed moment at the particular joint is equal to zero. When your undisturbed moment at particular joint is equal to zero, then you can say the values you are getting are the actual values of the moments that you are expecting at that particular joint. So by this, we have covered all the statically determinate as well as the undeterminate structure. And after that, I have introduced you to the one basic concept related to the direct stiffness method, in which how we can develop the stiffness matrix and what are the properties of the stiffness matrix. We have discussed, and one problem related to that, if you want, we have seen in the week 12. That is a very complex problem. Basic problem also related to that you can solve, and then this wraps up your course of structure analysis 1. I hope you would have liked this session as well as what we have covered in all the problem solving sessions in last 12 weeks every Saturday. I hope you would have liked all the videos, and whatever concept we are trying to provide you, I hope you would have understand as much as you can. And further, in case you are feeling any difficulties, we have feedback form provided to you. You can give your feedback form. It will be either good or bad. Depending upon your feedback only, we will try to improve the quality of work that we are providing you in every session or in every course. Your feedback is very important, because that only will help us in upgrading our skills, that in what place we are lacking, in what place we are good, and what we can do for the betterment of the course that is provided to you. So okay, so by this I will end this session. I won't make this session too long for you. I hope this session will be helpful for you, as well as all the 12 videos that is provided to you. Okay, so enjoy your day. Now do your NPTEL exam well for those who have registered, and for those who are not registered, all the best for your future. So thank you everyone. Have a nice day.